Hi everyone. I really wanted to do this in class with you guys, but missing class cannot be avoided today, so I'm just going to do a video recording of this. I want you to do this activity, by the way, before you watch the multiple comparison notes. That may be too late for some of you, and that's just all right, but I did want this activity to precede you seeing all the methodologies associated with it, just to spur the need within yourself for this kind of procedure, because many people misunderstand why we do multiple comparisons, and hopefully this activity will illustrate the need and the why behind it. So we have here results from a research study that considered the effect of a set of 15 medical conditions, or risk factors. I shouldn't say medical conditions, but risk factors on the incidence of obesity. So the research question guiding the analysis was, is obesity associated with these specific medical conditions? We did some tests to look at the association, and the p-values that appear result from, I'm calling them least significant difference t-tests. That's just more or less a regular t-test. Comparing those with the medical condition to those without the medical condition I have 4 populations. I should have typed that out. 4. I'll make edits to my handout as we go. The results of the analysis appear below. Let me move it up a little bit. So notice our 4 populations are young female, young male, old female. I sound kind of offensive here, don't I? Old male. And they're divided into these different groups, partly for illustration, but also just because it's presumed the investigators thought that there would be some difference according to the population. So spend some time. I did go ahead and highlight the p-values that are statistically significant below a 5% observed significance level, and take some time and just think about these results and kind of what kind of story they might tell to you. Then we'll move on. So pause the video, 30 seconds, think about it, and then we'll get to the rest. Okay, so how many comparisons are we making in total for this study? Well, we had, 15 medical conditions. So there's 15 things listed here. And then we have times 4, because we have 4 populations. So in all, we are making, I will type this out as we go, 4 times 15 equals 60. In class, you would have all figured this out on your own, and I know you can. And how many p-values are highlighted here? Well, let me make sure I count this correctly. We have 1, 2, 3, 4, 5, 6. So very simple here, just 6. P-values are smaller than 5%. Compute the proportion of p-values, significant p-values out of the set. So it's 6 over 60 or 10%, right? I'm not going to do or equal, or 10%. So we got about 10% significant p-values out of the full set. So if we want to calculate the overall or family-wise error rate, this is something you'll see in the notes. What it is it is at least 1 minus 0.95 to the 60th. We go into this in more depth in the notes, but basically, if we have 5% error, then we have a 95% chance of being right. So if we want at least 1 error in a set of 60 inferences, we need to take that 0.95 and say, okay, the probability of no errors would be 0.95 to the 60th. And 1 minus that would give you the complement to all questions, or all associations or p-values being correct, or all tests being correct. And so 1 minus that gives you the result that at least 1 is incorrect, okay? So notice that's right around 0.954, okay? That's just a coincidence here that, it's a numerical fact here, what I have stated, but there's no significance behind the fact that this is about 0.95 and this correct rate was 0.95. That That's just because this is 60, okay? That means for the entire set of 60 comparison, there's about a 95% chance that there's at least one null hypothesis falsely rejected, okay? And so we're pretty much sure to see a type 1 error in this set. If we were to take a Bonferroni significance level, perhaps you're familiar with that, we would take 0.05 and divide it by 60. So that becomes a very small number, right? And we can do that. And that's a very reasonable procedure to use, and one we're going to use right now just because it's easy. So what is this value going to be? It's 0.00083, repeating decimal 3, okay? So this means that each of our adjusted significance levels should be at this level. So let's go back. We want to compare each p-value back to this value. This Bonferroni adjusted significance level, okay? So in other words, instead of 0.05 for each comparison like we did at the outset of this activity, we're going to use this adjusted one, this Bonferroni adjusted one. And this will take into account that we're doing 60 inferences at the same time, 60 tests at the same time, and we'll reduce this risk because this is too high, 95.4. So it will keep that at 5% rather than 95.4%. So this is a very conservative test, by the way, so let's see what happens. Okay, so 0.0008, more or less. So if you look, our highlighted p-values, none of them are smaller than 0.00083, right? Does everybody agree? Email me if you do not agree, I guess, but it looks to me like everything's smaller. So now, when we use this, using this adjusted value results in no significant tests. Okay? So let's go back. All of you hopefully were able to construct some meaning behind the results here. I usually have students share in class, and I usually get something like, older females are, and females at general are more at risk than men, it appears. In particular, older females appear a little bit more at risk for obesity than younger females. Okay, there's a reason that this makes sense as an interpretation when we look at these results is we do see a lot more significant p-values for older and young females. We only see one for any male whatsoever, and it's very marginal, notice, and for the C-reactive protein. And we know that women tend to, I think women do have, well, they do naturally have higher body fat and tend to struggle with obesity, especially later in life, more than males. Okay, so this kind of, we can see a story from these p-values, and it kind of confirms what we think is maybe already true, a story, a narrative that we think is already true. So it makes a lot of sense. So people typically, when I do this activity, people tell a story that seems quite reasonable and doesn't sound wrong at all. Okay, but after looking and saying, oh, well, if we use a corrected significance level using something like Bonferroni, we get no tests. So then we'd say young, old, male, female, it makes no difference. There really is no association, it appears, with this effect of, the obesity. And so then it makes you doubt, okay? I have a little bit to share with you at this point because the fact that now I need to tell you a backstory of this data, these p-values that appear right here. The backstory is that this was a real study with these real effects associated with obesity and done, but these are not the p-values. what I did was I took the study idea and I created this table, and all I did was in R is I randomly generated values between 0 and 1. And so it's a uniform distribution between 0 and 1. So each of these values appear solely by random, by chance, I should say. And none of these values have any meaning whatsoever. Yet, at the same time, for every set of values I give you, almost all of us would be able to come up with a reasonable story, as we did here. And hence, I want you to see why it's so important that we control for multiplicity. If we only saw one effect, there wouldn't be such a convincing set of evidence for a certain thing that may or may not be true. Here, we know it's not true. The p-value distribution is totally different than this when you look at the results of the real study. It is not uniform 0, 1. Okay? And so this is kind of a cautionary tale of what can happen when you don't use multiplicity corrections. You come up with lots of spurious conclusions that are not based upon real effects in the data, but instead are based solely on chance. And so we need to be conscious of using them, especially in cases like this, when we've maybe created categories of data and are making multiple inferences as we are here. Now, how to control for multiplicity, and we'll talk about this later in class. I mean, do you control for multiplicity for each population? So only for young females, which would be 15, okay? And then separately for young males, that's an open question. That kind of depends on your experimental results that you wish to obtain. But hopefully this illustrative activity has kind of brought to light why we need to consider always using a multiplicity adjustment when we have multiple inferences or multiple tests in a study. Okay, so the very last question is, do you believe these results? Write 1 or 2 sentences for not believing these results. Maybe next time in class I'll reserve a couple minutes at the start of class just to talk about this. So if you have any questions, any concerns, or any like, hey, why did you do this to us kind of things, bring it up then. We can talk through this. But hopefully you'll come with a strong need to learn multiple testing, and we'll go over some of in class I actually want us to go over some of the detailed procedures. It's kind of long and laborious to do that, but I think it's best done in class. So we'll start with that on next class period, which will be Tuesday. See you guys then.